Um, yeah, thank you very much for the introduction. And thank you all for being here, and thanks to my committee especially for being here. I want to talk about some of the work that we've been doing in my PhD, specifically with the dissertation title here being Temporal Difference Learning for World Models, as Xiaolong mentioned. We'll be talking about, let me see if I can move this one. Yes. We'll be talking about the definitions of these two things. What is temporal difference learning? It's something that relates to time if you're not familiar. And then world modeling is kind of just modeling the world around us. So the AI agents that we have today, we're all using them. They are these like very generalist models. For example, this is a model from Meta AI where you can snap a photo with your phone and you can ask a question, for example, on how to decorate your room. And it will give you some pretty reasonable suggestions that kind of match the question and the image that you took. We also have very powerful video models where you can prompt them with a text prompt and it's able to generate high fidelity videos that match the text description that you requested. The general vehicle behind making this happen is that it's a single model, like a single neural network that has learned many different tasks just from passive observation of internet data. So a lot of internet data has been scraped and used to train this model. But there are some skills that I would argue are better learned by doing, especially when we move into the physical world. For example, here's an experiment of a robot experiment that we did a couple of years ago in the lab. And so here we have a robot with a dexterous hand, and its task here is to pick up the water bottle, reorient it, and then place it down on the table again. And if you take the first frame in this video and you prompt ChatGPT and ask it to give a very detailed description of the motions that would be required to do this task, it gives you a good high-level description in plain language that describes all of the individual steps. But if you look closely at the specific parts of the plan that it's proposing here, for example, the grip execution part, so grasping the bottle, it says the gripper closes around the bottle at the position that provides enough leverage to lift it without excessive force, avoiding slippage or damage. So it's describing it in accurate terms, but very vague terms. So it doesn't have a sense of which kind of grasp is best for this bottle, how much leverage do you actually need to lift it, how much force to apply to the water bottle to not drop it or damage it. And it's also not able to answer questions like this. So what happens if I apply just twice as much force to the water bottle? What would happen then? In the case of a water bottle, maybe not much would happen, but if you're picking up grapes, for example, it can be very detrimental to the grape if you apply too much force. So I've spent some time thinking about how humans reason about the physical world. We do it every day, mostly without thinking. For example, if we're picking up a book from a bookshelf, it comes very naturally to us, even when there's many different books, many different bookshelves, and sometimes it might be far up, so we have to reach higher for the book. We mostly just, when we do this, rely on like intuitive physics, heuristics, common sense, or just experience to do this task. I'm not a neuroscientist, but I would say that we're mostly not using equations or our understanding about explicit like physical law when doing these tasks. It's mostly just based on experience. And so that then begs the question of how do machines reason about the physical world, or how should they reason about the physical world? And my kind of like the thing that I've been working on and mostly in my PhD is the concept of world models. We'll be talking a lot about that today. The general idea of a world model is that you have a lot of interaction data with, say, a robot interacting in the real world. The real world has, a base real physics. So usually if you're like in a state perceived by the robot and you take an action A, you end up in a new state because the world has changed in some way. For example, the robot might have grasped the object, or it might have moved from, say, like point A to point B. So if we take all of this environment interaction data, we can feed that into a world model that approximates the real dynamics. So this is not an explicit model, so it's all data-driven, represented with a neural network. And so we don't know the real physics, but we can approximate it from experience. And now when we have such a learned world model, we can use that for planning or to imagine what would happen if we took certain actions in the future. For example, for a problem here with the bike on the road, if the task is to bike forward without falling, we could imagine many different action trajectories that might have different outcomes. The way that we use world models for control is that we define what we call a reward function, that is some function that if you maximize the function, you do the task that we wanted to do. And so the way that we do planning is that we can simulate many different futures, and then we can take the trajectory that maximizes this objective that we want. And one of the key things that sets world models apart from other models is that it gives us the ability to generate counterfactuals. So here's an example of a world model made by Google DeepMind, where it's simulating here this like 3D video game-like environment. So all the frames you see here are generated by the world model, and then the actions here are coming from the user interacting with the keyboard. So you'll see here that when the user presses W, the boat moves forward as expected. If you press A, then it turns left. So this is the idea of counterfactuals. So if you press different keys, the boat will do something different. So I want to talk a little bit about how to actually build these world models. Generally speaking, we have some kind of observation space. This is our input data space. So this might be, in the case of this dog here, it might be joint positions of the dog, or it might simply be an image of the dog. And we can encode this into a compact latent representation using a feature extractor. And then condition on this latent representation and an action, we can roll out the dynamics here in the latent space of the model. In order to train this model and make sure the dynamics actually behave like the real dynamics, we have some number of prediction heads or objectives that we use for supervision for training the dynamics, and also potentially prediction heads for different downstream tasks. We're going to see examples of reconstruction, which is generative world models, so explicitly generating future frames and using deep pixels as a predictor or as a loss. We're also going to look at self-predictive world models, which is the TD learning part of it that I've spent a lot of time in my PhD working on. And then also, if you want to do planning with the world model, you also train a reward hat so that you can do downstream planning. In the world model space, most of the research is happening on this higher level here. So what is the type of supervision do we need to train our models, and what are the kind of downstream applications we're interested in? And there's roughly two different classes of algorithms that people use. It's generative world models, with Dreamer being one example. This one is explicitly decoding images using a decoder that is trained. And then it's comparing the pixels that you predicted using the world model versus the ground truth pixels in the data. So this is very a pixel level prediction. And then the other class of algorithms are these self-predictive models like TD-MPC, which is what I've been working on. And so they don't have this decoder. Instead, they only predict in the latent space. And the way that we enforce the dynamics is to take the ground truth observation and code that into the latent space and then compare in that space. So the outline today will have 4 different parts. The first part here is I'm going to talk about how to actually build these world models that can be used for control. So this is the work on the TD-MPC line of work. And then we're going to look at how to extend this type of algorithm to now a not single task, but like multitask setting, where we do many different tasks using the same model. And then we're going to look at multi-domain learning, where we are taking this model that has been used in a multitask setting and now applying it to a multi-domain setting where there's not just control tasks, but video games and many other things as well. And then finally, I want to talk about some very, very recent work that we just submitted to NeurIPS, which is more on the generative learning side, but is explicitly trying to build world models that humans can interact with in an intuitive way. So I want to start by talking about TD-MPC. I've mentioned it a few times already. It means temporal difference learning for model predictive control. And the key idea here behind temporal difference learning is that for some environment here, we might have a robot in a specific state as one here, and we want to move to a goal location. So this is a task that we're now doing. And for this task, we might define an objective using a reward function that, in this case here, is like negative distance from whatever state the robot is in to the goal. And then we want to maximize this not just at a single time step, but over a sequence of time steps. The one thing that we have control over here is the actions that we're taking. So the environment dynamics we don't necessarily know, but we can plan actions or take actions that put us closer to the goal. The way that we might approximate this objective is using TD learning. And so, for example, if we're in state S1 and we take an action A1, we end up in a new state. And we can define the Q value, the value of being in this state and then taking this action as Q here of S1, A1 equal to the reward that we get at that single time step plus the maximum value at the next time step. And so this recurrent definition gives us a way to optimize the Q function using dynamic programming. And if you do that over many different state action pairs, you might get like this kind of value gradient, where in any given state, if you're in that state, you can query your Q function and figure out which action will put you closer to the goal. The problem with this is that the Q function that we're learning is estimated from data. So in areas where we don't have like good coverage, for example, our estimations might not be accurate. And it's also a neural network, and so they are inherently noisy. So typically the values that we actually get from our value function are putting us in the right direction, but with some noise. So the way that we're training this TD-MPC world model is that for a state S1 here, the first state in the sequence, we encode that into the latent representation. We predict some different quantities like the action to take in that state, the reward in that state, and then the Q value. And then condition the actions in the data, we can recurrently roll out our model and make these predictions. So as I mentioned, this is not a generative world model, so we don't actually decode the images. The way that we enforce the dynamics here is that we minimize this difference in latents. So we apply the same encoder here at every single time step. And then for, say, the last step in the sequence, we're minimizing the difference between the ground truth observation at that time step, if you encode that into a latent space, versus if you took the first one in the sequence and then roll that through the model, you get a different latent, and you want these latents to be similar. So you can write it a little bit more formally. Here's the exact equation that we're using. So there's an expectation here over the data set. There's a sum here across time, which is weighted, so that we are prioritizing the things that are closer in the future. And then we have three terms here that we apply each time step. So one is the joint embedding prediction. That's the self-prediction prediction objective that I just explained. Then we have reward prediction, which is supervised learning on the reward function. And then we have this TD learning objective. And we're optimizing all of these jointly. So once we have this world model, we can use it for planning. So this is the MPC part in TD-MPC. And the way that we do that is using sampling. So we can roll out many different trajectories from a state S1 here that we're given. We can roll out these different trajectories using the model. So this is entirely inside the imagination of the model. And then because we're learning this reward and value ahead, we can estimate the return of a given trajectory. And if you want to solve a specific task, we simply take the trajectory that maximizes our expected return. And so the way that it works for a single trajectory is that we encode it into latent space. We roll out the model here, and then we have this return estimate that is a combination of the rewards that we're getting from rolling out our model. And then from this planning horizon and beyond, we use the value function to bootstrap. So the model is pretty accurate in short horizon rollouts. So we're using the model for that. And then for anything beyond the horizon here, we're still using this a little bit noisy value function to estimate the long-term returns. So one way to use this world model is an online reinforcement learning setting. In this case, we're controlling this like dog-like embodiment in a simulation. The task here is to run forward with high velocity. So we have a reward function that is proportional to that. And then in the left image here, at time step 0, we have a randomly initialized world model, so has not seen any data before. And then we use the world model to do planning initially, pretty much random behaviors. We use that data to go back and train our world model, and then we again use our world models for more planning. And you'll see here that as you repeat this iterative cycle here, you get better and better performance. The caveat here being that 10 million steps is still quite a lot. So this is in simulation, so it's less of a problem. But if you were to do this on a real robot, this plain algorithm TDMPC here, you would have to run your robot for about 12 days without any downtime. So this is still pretty slow for a real robot. And so something that I've spent a few years of my PhD working on here is how to make robots learn faster directly in the real world without simulation. And here's some results from a couple of particular works that we did, where here we have a robot in a lab, again, the bottle task that we saw earlier. We have a success detector that is just binary, so it's detecting is the task solved or not. So we're predefining this success detector. And then the robot here, the world model and the robot is controlled using just plain RGB inputs. So there's 3 cameras in this scene here. There's one on the wrist of the robot. There's one in the background of the video you can see, and then there's the one that we were viewing from. And the way we were training here our TDMPC world model is that we collaborate our robot with 10 times, so 10 demonstrations per task, basically controlling the robot and doing the task for the robot. Then we're initializing our world model with that data, and then we let the world model interact for 1 hour completely autonomously. And the results are pretty interesting. We see here now we're plotting the success rates after training. And if you are running TDMPC from scratch just on a real robot, you get essentially 0% success because it's very unlikely that just a random policy will ever be able to succeed in any of these tasks. If you initialize the world model only with the demonstrations, you get 18%. So this is a lot better than 0 for sure. But it's failing to generalize to new positions of the bottle and the robot that is not seen before. And then if you let it instead interact for 1 hour in addition to the demonstrations, we get about 40% success. So this is a lot better with just 1 hour of interaction. The typical industry target, if you actually want to apply this to a real factory, is much higher than that, but this gives us a framework to learn from experience. So with that, I want to move on to the more scaling experiments that we did. So the follow-up work that we did, TDMPC2 here, is a direct second iteration of TDMPC1. The algorithm essentially works the same, but there's some slight differences. The reason that we decided to do a TDMPC2 here is because we're working with real robots for a couple of years and different applications. And what we saw time and time again is that when you have a new task or a new application in mind, you might actually have to tune the algorithm quite a bit to work well on that specific task, because tasks are just inherently very different. One particular example of that is the reward scales for different tasks that are used. In the bottle example, because we have this sparse task, where it's 1 if we solve it task and 0 otherwise, the range of rewards is pretty low. But if you take this algorithm and you apply it to something like Atari, there are some games here where the range here is orders of magnitude larger. And this means that if you're training things, you're doing TD learning, for example, with a mean squared error objective, in this case, it's reward prediction, you see that the loss here actually scales with the magnitude of R. So if you make your reward function larger, the gradients become larger, and this leads to training instabilities. So this is one of the reasons you have to tune your algorithm. And so there's many ways to solve this. We picked one pretty common way of solving it is just to recast the mean squared error objective here to a classification problem. So using discrete regression. The way you do that is that you bin the target values into a one of many bins, and then you simply do classification in that space. The nice thing about this is that it doesn't scale with R, so it's agnostic to the actual reward that you're getting, and it's also bounded. So the optimization is much more convenient. And to demonstrate that this actually does help, and allows you to apply it to many different tasks. We run a big experiment here with more than 100 different tasks in different simulators here. So this is there's a lot of videos of locomotion, manipulation, and so on. And we're able to apply this algorithm without any tuning, so just applying it completely out of the box. We have divided the task that we did here in 6 different domains where we also have the normalized score and the y-axis. So this is what we want to maximize. And 100 normalized score, for example, might translate to a success rate of 100% in a manipulation task. So we compare against some different algorithms like Soft as a Critic, Dreamer V3, and I think the most interesting comparison is the first iteration of TD-MPC. So this TD-MPC result was actually tuned for all of these tasks, which is very, very tedious. With TD-MPC2, with these new changes that we made, we're able to match or beat that performance without any tuning. So this is a big step up if you want to apply it to something like a real robot. And it turns out that even making things robust in a single task setting directly also translate to a multitask setting. So we also collected a big data set of 80 different tasks that we did, an offline data set. And then we scale here to now the model parameters on the x-axis. And what we see is that for this fixed data set, making the model bigger tends to give better performance. And this is particularly interesting in a multitask setting because when you're doing multitask learning, you have many different tasks of different reward scales, and we need to be robust to those differences. The first iteration of TD-MPC did not scale, mostly because of these training instabilities. So moving on to the multi-domain experiments. The tasks that we did before are all like these DM control meta world experiments. And we wanted to stress test this algorithm and try to apply it to many different domains at the same time. So this is just showing some of the diversity in the tasks that we did. Some of them are control environments, some of it is locomotion manipulation, some of it is navigation. There's a lot of video games, Atari games, and so on. So very diverse set of tasks. And the question they were asking is, can we train a world model to perform all of these different tasks? The challenge with making this happen is that the RL environment landscape, the environments that we have available is pretty scattered. So there's many different open source environments like DM Control, MetaWorld, and so on that we have seen so far. But all of them have maybe in the order of 10 to 50 tasks. And so we can do multitask learning within a single domain, but actually extending it to many different domains is really challenging. So we spent a lot of engineering effort trying to make this happen, build a single API that supports all of these different environments. We ended up supporting 200 different training tasks, all of them with reward functions and everything. These spans across 10 different task domains. Many of them existed already, and some of them are completely new. And then we collected a lot of demonstrations for all of these. So like in the robot examples that we saw earlier, we want to initialize our world model with demonstrations to get good exploration, good convergence, and then do online interaction after. We also support a lot of the other things. We have checkpoints and everything. So it's also great for other kinds of research problems. This is showing the diversity of the task in a more structured manner. So these are the specific task domains that we worked with, and you'll see that they vary quite a bit in the specific embodiments. So we train a world model using all of these 200 different environments. We first pre-train on our demonstrations, and then using this API that we built here, we interact with all of these environments at the same time in parallel. In the environment here gives us state observations. So this is a low-dimensional vector with, say, joint positions. And then because these different tasks have different dimensions, we kind of just zero pad to make things fit. And then we also have image inputs, so observations here, like the images shown. And we feed that into our world model that we called Newt. And then we also have natural language descriptions that describe both the embodiment that we're controlling and also the task that we're trying to solve. And so feeding all of this into the world model then is able to do planning. So we're producing sequences of actions using sampling that also are masked because some tasks and some embodiments just have a higher or lower action dimension. And we're also predicting rewards like we talked about before. Under the hood, the algorithm that we're using is mainly just TD-MPC2. The main difference here is now that we are conditioning on both state, images, and text. So if we redo the benchmarking experiments that we did before, now in this multitask setting here, we see that if you only use demonstrations, you get about 18% success again. We tried a couple of other algorithms. They're kind of in the same neighborhood. We tried TD-MC2 from scratch. So this is without the demonstrations, just running it from scratch. And then we also tried Newt here, which using all of the different components, the different inputs, and also using the demonstrations, we're able to get better performance. So in this last part here, I want to talk about a slightly different type of world model. So now we're moving on to talk about generative world models. And one of the things that make these models really appealing is that you can interact with them directly using, for example, a keyboard. This is kind of ongoing work. We submitted it to NeurIPS 1 or 2 weeks ago. But in general, in the generative world modeling space, we've seen a lot of efforts recently in scaling up the models and therefore also the capabilities of these models. And this allows us to do pretty long horizon interaction as a human. So here's a video from a world model that we trained recently on the benchmark, so the 200 task benchmark. And here you see me interacting with the world model using the keyboard. And so when I press a key up, for example, then the robot is moving in that direction. And similarly for these other 2D navigation problems that might be a little bit easier to visualize, we also see here that I'm controlling the yellow dot. The goal is to move to the red dot, but I'm controlling this thing using the keyboard. The problem with these models is that they still very frequently so-called hallucinate. By hallucinate, I mean that they produce futures that are visually plausible, but the dynamics are not. Some examples in the point navigation task here is that it might sometimes move through the wall if you're trying to penetrate the wall. And in other examples here, like in this example with a cup and then a ball attached to the cup here, you see that if you move to a specific region in the environment here, then it kind of like hallucinates the ball inside the cup. And we also find that hallucination is just that not something that just happens with small models, it also happens at scale. In order to support the study that we did here, we scaled up the MMBench data set. So we have something that is now 16 times bigger. And we also similarly scaled the model up accordingly. So the model that we trained here is 350 million parameters. And we see that the hallucinations that we saw at small scale also happens at this bigger scale. Specifically, we find that hallucination is actually an issue with the training data coverage. So models tend to hallucinate when they don't have data for that area. One specific example here with the navigation task, we can plot the state density because now we're in 2D, so it's easy to visualize. And here the dark blue means that there's high state density, and then white here means that we have no data for those states. And what happens then is that we can also plot different uncertainty metrics that use just the model itself. So basically trying to explain how uncertain the model is about its modeling in that specific state. And what we see here is there's a very direct correlation between areas where we don't have data coverage and where the model is uncertain. For example, here in this circled area here is where we previously walked through the wall. So the key idea in this work basically is to try to predict when the model is uncertain and then just collect more data in those regions. And we find that even with just as little as 50 trajectories, we can, in most of these tasks, significantly reduce the hallucinations that these models are making. In this maze environment, again, here we have on the left, we have the ground truth environment. So this is the real environment that we're collecting data from. And then in the middle, we have the base model that we trained. And then you see here that it's penetrating the wall here. And then in the last example, we have the model after these additional 50 trajectories that have been targeted specifically in the areas where the model was making mistakes.
So what do
Mhm.
these 50 trajectories look like if you cannot go into the optimum?
Yeah, so I don't have the visualizations here, but basically they are concentrated around the walls in this example. So that's where, for example, there's most of the penetration errors was happening. There's also like specific corners of the maze, like up here, that the model has not seen as much, and so it tends to move up there as well.
But then if I change the, optimal positions, you think it will wrongly, extrapolate?
So I think one of the reasons that it's penetrating this specific wall is that we are training on many different mazes, and some of them don't have a wall here. And so it might be extrapolating incorrectly. Yeah, that's a good question.
But I think question from Sean is more, to what degree can you generalize?
Mhm.
You know,
There's different ways of generalization. I think so for this maze example, you can give them a different maze and it's able to simulate it, but specifically with like the walls, for example, sometimes it might make mistakes like this. Because it's seen many other mazes where you can walk, on this path, and now in this example you can't because of the wall. So it might tend to like penetrate in those examples, but other than that, if you're not touching the walls in this maze environment here, you can actually still control the agent. But then if you're like generalizing to a maze with completely different dynamics, where now you have like gravity, for example, then it wouldn't know about that and probably would not model those dynamics.
Like in a new environment, you're given a map. Is there a way you can impose such constraints into the one model?
I think so. The model operates just from vision at the moment, so just RGB inputs. And
The
so,
model already sees the map.
yeah, it sees like the image that we were seeing here.
Okay, so I mean, I guess if it already sees the map, then it should already have this physical boundary conditions in, right? But it still
Mhm.
predict trajectories that penetrate the wall. That is like very, I guess in practice, that's frustrating, imagine you deploy a robot, you, at some sort of factory, and then you already told them, this is, where the blocks are, basically.
No, I agree. And I think that's partly like a data scale thing. So I think specifically for the maze environment, we have about 5, 10 mazes that it's seen in training. And so like sometimes it's able to generalize and sometimes it's not. But maybe if you have every single combination of mazes in the training data, it should be able to do it.
I don't think scaling data is the best solution here, right? Because it's expensive to collect data, and when you have data mistakes, collision cost will be much higher. If, what do you think of ways to, to tweak your algorithm somehow and impose some stress from this?
I think there's different sources of data. So in the experiment that we did here, all the data is directly like interaction data. But you could imagine that you could pre-train your world model on a lot of like video data that is just scraped from the internet, and then use the general physics understanding and perception of like these, large pre-trained models to then fine-tune on your specific problems and learn the action component as well. That's one possible way to get more generalization.
but I think, Nicola, I'm hearing, well, say, could you imagine that if you had different costs for collisions and things like that, you could have a way of training it so that it's not, right now it's purely
Mhm.
kinematic almost. And because of this, it doesn't really, it's not clear you're learning patterns of that. Collision is bad and free space is good.
Mhm.
That would sort of allow you to generalize. So it's generalizing purely based on the geometry and not based on a root cause.
Yeah, I think that's true.
But could you change your value function to make it generalized beyond geometry?
That would definitely be interesting. I think the answer is yes. I'm not exactly sure how. I think in this specific example here, it's like a human interacting with the world model. But if you're defining like a reward function for this task, you could, encode that you want to move to the goal, but also without like hitting anything. So in this example here, I'm specifically walking into the wall because I know that it tends to behave this way.
But you could imagine, like, when you do collisions, it will actually slow you down. So it could be time, it could be force, there's a number of factors that could be interesting.
Yeah, for sure, for sure. Yeah, I think it's kind of like an interesting planning problem because, many trajectories are feasible, but some are preferred, even if they're like getting the same reward. You might
Exactly.
prefer one motion or behavior over the other. Yeah, I think those are very interesting questions. The model here now, I just showed examples of these 2D maze problems mostly, but the model here is still trained on all the other data that we saw from Bench that's able to simulate these many different environments with pretty high fidelity. We do see here that for some tasks it's very, very accurate, and for other tasks we still see hallucinations. For example, in this example here, the agent kind of like disappears at some point, and also up here it also simply gets stuck. So hallucinations are definitely an issue even at this scale, but we do have a very concrete way of trying to patch the world model using additional data. So to conclude, we've talked about how to build world models specifically for control, so the TD-MPC-like environments, the TD-MPC-like world models, and how to use them for control using planning. We have seen how we can scale those up to multiple different tasks in a single environment. And we've also looked at these multi-domain learning problems. And then finally, we talked a little bit about the interactive world models where we're explicitly generating images and the human is interacting using the keyboard. If you're a student and you're interested in this kind of research, then we did recently publish a paper, our new paper here. There's a QR code on the slide. And in this paper, we have almost 2 pages full of just research ideas that I think are super interesting. I just don't have time to work on all of them. One particular direction that I think is super interesting in light of all this like hallucination research is to try to develop models that not just like models that are aware of the knowledge gaps that they have. So the model might know that it's entering a state or a region of the state space that it's uncertain about, and then either it can prompt the user, for example, for guidance, or it can simply just refuse to enter those regions. And all of the work that I've talked about is open source. So the link here, tdmc2.com, has code for training and evaluation. We have all the checkpoints for virtually all experiments that we ran, and we also have a lot of data. So I didn't have time to talk about all of my research. This is the full list of publications, with the yellow ones are the ones that I had time to talk about. There's also a number of papers that are under review, which hopefully will be accepted within the next few months. Some examples of the work that we have done in like other applications of these TD-MPC algorithms is, for example, tabletop manipulation in this kitchen environment that we have upstairs in third floor. We also have done world models for humanoids, where now we're controlling the whole body of the humanoid here in simulation. And in this case, also it's using vision to avoid the different gaps. We've also been working on autonomous racing, which I think is a really interesting application because we've been able to collect human driver data from expert human drivers and compare their driving behaviors to the TD-MPC world models. So all the papers are available here on my website. You can go check them out. So I want to slowly wrap up the presentation, and I want to initially acknowledge my PhD advisors, Professor Wang and Professor Su, for all of their guidance during my PhD. They initially encouraged me to explore new topics. I was working on something else before my PhD, and we all agreed that world models would be super interesting. As Xiaolong mentioned, I started working on world models before it was popular, and it didn't really work back then, but it seemed like a really interesting academic problem. And now, years later, everyone knows what a world model is. I also want to thank my committee members, Professor Christensen, Professor Yu, and Professor Gao. We've also had a lot of good discussions over the years. I want to thank specifically all my collaborators that I've worked with pretty directly at different times in my PhD. It's been a really good experience working with so many different people that do very different things. And I definitely could not have done all the robotics experiments without some help. I also want to thank my lab members. We have, have a lot of technical discussions over the years that I think has been really helpful, especially in the early stages of my PhD. We've also done a lot of social events, like here we went bowling recently. Unfortunately, I'm not in the picture, but I promise I was there. And we've also done, various other events here at Xiaolong's house in this picture. I also want to thank all of my friends, many of which are here today. So I made a lot of friends in this building, mostly on third floor. And Paul, unfortunately, was not in this picture. Also a good friend of mine. He actually drove down from Pasadena to be here today. I also want to thank all the other friends that I've made around San Diego. Kalani and James also up in Santa Barbara. Friends that I've made during my travels and my internships in different cities. In this example, we were up hiking in somewhere in Seattle. And all of the friends that I've made down at Scripps through Clara. So yeah, I really appreciate all of you, and this has made the journey much more enjoyable. I also want to thank my family. This is a picture from 1 or 2 years ago, and when I visited my family in Denmark. They've also been supportive from afar for many, many years. I'm not going to say how many. My family has also visited here in California a couple of times, and that's been a really good time mostly in national parks. I also want to thank the newest member of the family, my partner, Clara. These past 2.5 years have been really, really enjoyable, and we've done many fun adventures together. Yeah, I appreciate all your support. We also went to the Renaissance Fair recently, and that was really fun. But yeah, thank you all for attending. I appreciate you all of you being here. And yeah, let's have some questions.